And of course, you could try to simplify the answer, but that's it. So the derivative of 7 is 0. The derivative of the square root of x is 1 over 2 times the square root of x. So that's that.
But that's the same. So you just use that solution right there. F divided by 2 right there.
Yeah, use the quotient rule.
I just want to make sure.
Yep, these examples 4, 5, and 6 all use quotient rule. Part of 5 was just linearity of the derivative and pulling the half out, you know. Like I only use the...
How do you know when to use quotient?
Need to use the quotient rule when you have a quotient. Need to use product rule when you got a product. But that is not actually, that's not a dumb question at all, because there are things we can look at as a product or as a, I mean, there's different interpretations. In fact, I would not usually use the quotient rule to differentiate Cauchy. I would usually use what's called the chain rule, which is our next topic. Now, we will be doing more examples of all of these, all right? And I'm not going to prove the chain rule today. I'm going to save the proof of the chain rule to next class, okay? But I'm going to state the chain rule for us this class, okay? So what's the chain rule? Like a chain? It must be like, so if the product rules for a product of functions and the quotient rules for a quotient of functions, or when there's a fraction, right? The chain rule must be when there's a chain of, what's a chain of functions? I don't know. Multiple functions. Yeah, I mean, so what this really should be called is the composite function rule, okay? Because that's what it's for, composite function rule. DNA chains. Oh no, no, none of that. No. No, we don't need to get any kind of. Don't need any kind of like permission for experimenting on human subjects or anything in here. It was just math. The only thing that could possibly be harmed is ideas. But don't worry, they'll be fine before us. They're going to be fine after us. Math really doesn't care what we do to it, but we should try to do it right. Anyway, d dx of f of g of x is df dx evaluated at g of x times dg dx. An alternative notation for this is it's df dg times dg dx. That's a notation which is sometimes used. Oftentimes you see this with the letter u, so like f of u of x is df du times du dx. You see that a lot. A lot of people like to use u for the inside function here. And then there's also the prime notation, like so f composed with g prime of x. And the prime notation is nice here. F prime of g of x times g prime of x. So in some sense, I like the prime notation even better here. So what is this? This is the derivative of the outside function f evaluated at inside function g. This one here is just the derivative of inside function. And when we have a composite of two functions, it's clear there's an outside function and there's an inside function, right? So you shouldn't get these two confused, really. Example. I'm going to start with d dx of e to the minus x. This is what I was just talking about. I would usually use the chain rule for this. So let me just be explicit here. I'm thinking u equals minus x, right? That's the inside function here. Or if you want me to be, let me be totally boring. F of x is e to the x. G of x equals minus x, right? If we let f of x equal e to the x and we let g of x equal minus x, then that is f of g of x, right? And so we use the quotient rule, which is f prime of g of x times g prime of x. But here, that is, notice that f prime of x is what? It is e to the x, right? And what's g prime of x equal to? D dx of minus x, right? What's d dx of minus x? What's g prime of x equal to? Minus 1, right? Put you out of your misery. The derivative of minus x is minus 1. I think you knew that. So this is minus 1. And what's f prime of g of x? So I could write it as this way, e to the g of x, right? Times minus 1. What is g of x? Minus x, right? So the answer is minus e to the minus x. So I don't think much is gained by writing it like f of g of x. I think a much better strategy of notation when you're starting to learn is saying u equals something and working like that. So let me do the same example again, but in the u notation. So I'm looking at d dx of e to the minus x, right? So I'm going to say that's d dx of e to the u. I'm letting u equal minus x. All right? The chain rule says what you do is you do the derivative of the outside function, which here is just e to the x, right? But e to the u is the derivative of the outside function evaluated at u, times du dx. But du dx is minus 1. Right? But then what is u? Well, u is minus x. So I don't know, I like this system of notation as a way for you guys to do it more than writing out f of g of x like that. It just tends to go better. Yeah. Right. You're like, one more and this will be it for today. 8 d dx of the sine of x squared, all right? So we go, okay, well that's d dx of the sine of u, right? Where u is equal to x squared. So that is cosine of u times du dx, because the derivative of sine is cosine. But I don't do cosine of x, I do cosine of u because it's sine composed with u. And du dx is what? It's 2x, right? So what I get is cosine of x squared times 2x, which I prefer to write as 2x cosine of x squared for reasons of mathematical etiquette. I don't know, it's really not It's like arguing what kind of spoon you use for salad or something, you know, but I like to write the 2x first. X squared did not become, well, I differentiate x squared to give 2x. du dx is 2x. Because the derivative of x squared is 2x by the power rule. Which you guys already know from test 1. Everyone got 100 on it, right? You guys get 100 on test? I mean, I hope not, because 100 out of 140 is not great. Yeah, there's 150 points to get. I mean, there's 10 bonus. That epsilon delta thing at the end was bonus. Mm-hmm. Oh, the ninja thing. Ninjas aren't bonus. Ninjas are required. Anyway, that's it for today, guys.